Okay, so let's begin this lesson by defining what a vector is. What do we mean when we talk about vectors? Now, in order to define a vector, we first need to compare vectors to what are sometimes referred to as scalars. Now, we deal with scalars all the time, especially in a math class. And a scalar is just any quantity that has just a magnitude, or you can think of that as just being, one number used to describe it. So example, or just any real number that you can think of as a scalar. Distance is an example of a scalar. So if I talk about, if I say something like 15 meters or 230 kilometers, that's a scalar. Speed is another example. I could talk about something in kilometers per hour or miles per hour, and that's an example of a scalar value, as well as mass, kilograms, pounds, whatever it might be. Temperature is another example of a scalar. Notice that although these numbers might have units associated with them, they're described by a single number. A vector is a little different. A vector has both magnitude and direction associated with it. So an example of that is what's called velocity. As soon as you take a speed and you assign a direction with it, you've now created a vector, and the term that we use for that is velocity. So there is actually a difference between the word speed and velocity. Sometimes we describe wind, for example, using velocity. We might say that there's a 30-kilometer-an-hour northwest wind, and so we're assigning a direction with that speed as well. Anytime you talk about forces, gravity, is 9.8 newtons, and it has a direction towards the center of the earth. And friction as well, another force that has a direction, and there's lots. If you've taken physics already, you're going to find that there is a bit of overlap between physics class and the beginning of the vectors content in this course. So if you're familiar with free body diagrams and those kind of things, that is going to help you a little bit in this course. And if you're not, that's okay too. And we'll learn about forces as well. If you don't know much about them, that's fine. Displacement, again, another physics term. As soon as you take distance and assign a direction to it, we use the word displacement, and it is now a vector quantity. So I might say that I, moved a box, 3 meters east or 3 meters up. I assign a direction to it somehow. So that's the difference between a vector and a scalar. We're going to start our study of vectors by talking about vectors geometrically. When I say geometrically, I mean using a picture. So right now, our vectors will all be directed line segments, okay? Sometimes called a ray. And our vectors will be basically drawn on a page or in a diagram. Now that diagram isn't to scale necessarily, but it's a picture for us to work with. And as soon as we draw a vector, we can talk about two parts of the vector, and that's the head and the tail. So we've got the head of the vector, and we've got the tail. Okay. Now I've got two vectors drawn on my page, and there's a couple ways that we can name vectors. It's very common to name a vector. We're going to use u and v quite a bit. So v, I'm going to call that vector v. Now the symbol for a vector, we just do a little arrow or a little half arrow like that. So there's vector v with that little half arrow. Sometimes you might complete the arrow as well. So you might also write vector v like this with the entire arrow like that. Okay, either way, it doesn't really matter. V is very common, of course, to use as a vector name. U is also very common. I find U and V can be a little annoying though, because U can kind of look like a V sometimes. A and B are common to use for letters as well. X and Y as well. Always lowercase when we name vectors like this. Another way to name a vector is if the vector sometimes will join 2 points together. Let's call those points A and B. And we normally use capital letters when we have points in diagrams. And so now we can talk about this as being vector AB. I'll do my little vector symbol there. Now notice that this is vector AB, not BA. So when we say AB here, it's implied that that means the vector going from point A to point B. So this vector is directed towards the bottom right of this page. Of course, this vector is to the top right of the page. This is a special vector. It's called a point-to-point vector. Okay, so two ways to name a vector: a point-to-point vector, AB, or just calling a vector by a single lowercase letter like V or U or A or B. And you can go back and forth between the two different notations if you want. Vector has magnitude and direction, so how do we define magnitude or express magnitude and direction geometrically? Well, it's probably exactly what you'd expect. The magnitude of the vector is just the length of the line segment. The longer the line, the higher the magnitude of the vector. How about the direction of the vector? Well, that's the direction in the diagram. For example, I might refer to this vector as, pointing the top right of the page and this the bottom right of the page. So the direction sort of depends, it has to be a reference to something else. That something else could be another vector on the page. It could be that we have a northeast, southwest coordinate axis somewhere. Could be that it's on the Cartesian plane, XY plane. Those are all possibilities about direction. Now, this will sort of become more apparent as we look at some diagrams with vectors in them. Do keep in mind too, just because we're drawing a diagram doesn't mean it's to scale. So you can't, you're not actually going to get a ruler out and measure these, but the length of them in the diagram refers to their magnitude. Now, notationally, it's important that we talk about that as well. And what I mean is, if I want to talk about the magnitude of vector v, I can use there's a notation for that. So I've got vector v, okay, and when I just have this symbol here, that just refers to vector v. Now, v is not a number, so you can't say v equals 5 or v equals 10. It's a vector. It has a magnitude and a direction. So v is a picture right now. If I want to talk about the magnitude of v, the symbol I can use are the absolute value signs. So this is how I can talk about the magnitude of v. So now I could say that this is equal to 3 or 10 or 20 kilometers an hour or whatever it might be. And of course I can do the same thing with vector AB. Throw the magnitude signs around it. Okay, just like that. Sorry, I know it's painful to watch me write that so slowly. And there's the magnitude of AB. Now it's important to talk about too, when we talk about direction of a vector, the direction of a vector might be made in reference to something else, like another vector. If we give the angle between two vectors, it's assumed that that means the vectors are placed tail to tail. So if I talk about, two vectors, and I say that vector A and B have an angle of 30 degrees between them, that means that the vectors are placed tail to tail. And as you can see there, I've drawn those two vectors A and B tail to tail, and the angle between them, which we often call theta, is when they're placed tail to tail. Now notice that vectors have magnitude and direction. They do not have position though. That means that you can move a vector wherever you want it to be. So any two vectors, even if they're not drawn tail to tail, you can move them so that they are tail to tail because they don't change when you move them. They don't have a position on the page. They just have magnitude and direction. So just keep that in mind. It's very important. I'll try to remind you about that as we go on, that the angle between two vectors is the angle made when they're placed tail to tail. Okay, next we're going to do some examples where we look at some diagrams in pictures, and the goal is to find the magnitude of vector u in each picture. Now I apologize, it looks like vector u got cut off in this printout, but there's vector u, we're going to say is this the only vector here with that arrow there. Now we're not finding vector u, there it is right there, we're finding its magnitude. And while we're doing some vector work, we're also going to be reviewing some trigonometry because you need trigonometry to solve each of these questions. So if I look at this diagram right here, I can actually see that I have two similar triangles. The big triangle right here and the small triangle up here. Now the reason they're similar is that all of their angles are equal. They each have a 50-degree angle, and then this angle here is like they share that angle. So it's the same, and then of course these two angles must be the same as well to add to 180. So because the triangles are similar, the ratio of their sides, corresponding sides, are equal as well. So basically one triangle is just an enlargement of the other. So the magnitude of u divided by 4 would be equal to, let's see, so this side divided by this side would be equal to this entire side, 5. divided by the small side, which is 2. So 5 divided by 2, or 2.5, basically tells us that the big triangle is 2.5 times bigger than the small one. Just a matter of solving this. It must be that the magnitude of u is equal to 5 times 4 divided by 2, which is equal to 10. So we know the magnitude of this vector is 10. Now we don't have any units, but that doesn't matter. And you also see this idea that, we were able to calculate the magnitude of u by figuring out how big this side in the triangle must be, even though the picture wasn't drawn to scale. Okay, let's look at the next one. Okay, so looking at this diagram here, you can see that we have a right-angled triangle with 3 vectors. Now, 2 of them don't have names, but the vector u is the one we're looking for here. And they're arranged, notice those are actually arranged, these 2 are arranged head to tail, these 2 are arranged head to head. It's not uncommon to have pictures like this when we work with vectors. Since it's a right-angled triangle, we can use Pythagorean theorem. So it must be that the magnitude of u squared is equal to 12 squared plus 5 squared. 12 squared is 144, 5 squared is 25. So we get the magnitude of u squared is 169. And it turns out to be a Pythagorean triple. So the magnitude of u must be square root of 169 is 13. Looking at the picture on the right, okay, notice that we have side, angle, side, and we're looking for the opposite side here. This is an example of when you can use the cosine law. And you're going to find that in this course at the beginning, we use the cosine law quite a bit. So let's get started. The cosine law, of course, is something like c squared equals a squared plus b squared minus 2ab times the cosine of c. And if you need to see a little bit more about the cosine law, if you just look at page 121 of your textbook, the cosine law and the sine law are there, and there's some review questions I'm actually going to have you do as well. So in our example, c here is, of course, the vector u, and then, of course, angle c is across from side c. So we just fill these values in. So the magnitude of u squared will be equal to 2.3 squared plus 5.1 squared. Subtract 2 times 2.3 times 5.1 times the cosine of 34 degrees. Now from there, if you just use a calculator, you should find that you get the magnitude of u to be approximately 3.4 units. Okay, we can't do exact values here because we don't have a nice angle. And notice when we talk about vectors geometrically, we do use degrees. We don't use radians. We'll use radians in the calculus portion of this course, but we use degrees when we talk about geometric vectors. Let's talk about some more properties of vectors. I sometimes think it's helpful to imagine that we've invented vectors as a way of describing things, a way of describing forces and wind speeds and directions and all that kind of stuff. And so we start at the very beginning about what does it mean to do certain things with vectors or describe vectors. So what is equality of vectors? What does it mean if 2 vectors are equal? When can vectors u and v be equal? Well, it's not a very surprising definition. Obviously, if u and v are equal, they should have equal magnitude. So basically saying that vector u's magnitude needs to equal vector v's magnitude. But just because vectors have the same magnitude doesn't mean they're the same vector, doesn't mean they're equal. They, of course, should have the same direction as well. And then once we do that, we can say that vector u is equal to vector v. Now, because we have u and v, the vector symbols here, it's implied that this equal sign means vector equality. So we use the equal sign in math all the time, basically saying, hey, look, we're going to be allowed to use the equal sign when we talk about vectors. Okay. Now, there's another little trick here too. Notice it says 2 vectors u and v are equal if and only if. So the if part means if these are true, then the vectors are equal. The only if part means that if the vectors are equal, that these must be true. So it kind of goes both ways. If you have 2 vectors that are equal in magnitude and have the same direction, then they're equal. If 2 vectors are equal, then this must also be true. And we'll talk a little bit more about that as we go on in this course as well. We can also talk about the negative of a vector. It's kind of like the opposite of a vector. So the negative of a vector is a vector with the same magnitude but opposite in direction. So we can imagine that geometrically. Suppose you have vector A, and you want to talk about the negative of A. It would be the exact same vector but in the opposite direction. And we will use the negative sign. So we could say, talking about, there's a sort of a regular vector, but how about a point-to-point vector? The vector going from point A to point B. So the negative of AB would be negative AB. But think about what that picture would look like for a second. If you've got vector AB, then negative AB goes the opposite direction. So instead of going from A to B, negative AB would go from B to A. So negative AB is actually equal to just the vector BA. And this little, little thing that I've written here, it actually, that's actually something you could do right away. If you saw negative AB, you could immediately write that must be vector BA. You wouldn't need a picture to know that that's true. There's also such a thing as the zero vector. The zero vector has a magnitude of 0 and its direction is undefined. It's the only vector that doesn't have a direction. And the symbol we use for the zero vector is a little vector sign over the 0. Okay, in this next example here, we've got a parallelogram ABCD. So opposite sides are parallel and they also have the same length. It's very common in this course, again, to actually, we will deal with parallelograms quite a bit, and we will have vectors in parallelograms. So find a vector equal to AB. Well, here's vector AB. Vector DC is parallel and have the same length, so therefore vector DA is this side from D to A. Well, CB is the exact same vector, so that is equal to CB. Notice it's not BC, it is CB. BC would have opposite direction. Okay, negative CD. Well, one thing I could do right away, without even looking at the picture, is I could say that this is DC. Okay, which is also AB. So a couple different options there for that one. Okay. Find vectors equal to the negative of AB. So not the same vector, but the negative of it. Well, again, one thing you could do right away is you could say BA. You don't even need to see a picture to know that BA is the opposite of AB. And then another example using the picture. Okay, so if AB goes this way, then the negative of it goes the opposite way, which is CD. So CD is another possibility there. Notice I'm not saying equal because they're not equal. They're negatives of each other. CB goes like this. So the negative of CB again could be BC, sort of a cheap one to choose that. DA is the negative of CB as well. So DA or BC are really the only answers you could give there for negatives of CB. With numbers or scalars, we can perform operations on scalars. You know how to add, subtract, multiply, divide. We do the same thing with vectors. So as this course goes on, we're going to talk about operations on vectors. We've talked about what it means for vectors to be equal. We've talked about taking the negative of a vector, and we've talked about the zero vector. We can add and subtract vectors. We're going to do that not in this lesson, but the next. And there are actually a few different ways to talk about multiplication of vectors. Actually, 3 different ways that we could refer to multiplication of vectors. We'll do one of them right now, which is the simplest, which is called scalar multiplication. So recall that a scalar quantity can be any real number. A vector can be multiplied by a scalar. So our vector v can be multiplied by a scalar k to produce a new vector kv. So when you take a vector and you multiply it by a scalar, you call that scalar multiplication, and you get a new vector. That new vector has 2 properties. The first gives its magnitude. So kv is a vector. Its magnitude is equal to the magnitude of vector v times, notice that this isn't the magnitude of k, it's the absolute value of k. Since k is a scalar or a number, these 2 bars beside it now refer to absolute value. So for example, suppose you've got vector v. You can talk about, for example, vector 3v. 3 times vector v, that's scalar multiplication, would produce a vector that has the magnitude of 3 times vector v. So if vector v had a magnitude of 2, then 3v would have a magnitude of 6. Just make sure that that notation, you're comfortable with that, and why I'm kind of referring to these as now being absolute value signs and these as being magnitude signs. As for the direction of 3v or kv, the direction of kv is the same as vector v, provided k is greater than 0, and opposite if k is less than 0. So if I were to again look at this picture, here is vector v. Vector 3v would just be 3 times as long. Okay, if you can imagine that vector being about 3 times as long. And it would have the same direction. If you talked about, say, negative 3v, well, that would just be in the opposite direction, which we kind of already know because we know that negative v has the opposite direction. So it would make sense that that's what scalar multiplication does when you have a negative number. In this next example, we'll just kind of ensure that you understand a little bit about scalar multiplication. So here in this picture, I've got points A and B, which creates the point-to-point vector AB. Suppose that M is the midpoint of AB. So M is right here, and it's a midpoint, which cuts that vector in half. Okay, don't need to draw those, I might take them out. Okay, express each vector below as a scalar multiple of another. So for example, vector AB is really vector AM, but twice as long. So we could say that vector AB is really 2 times vector AM. How about vector BM? Well, vector BM is, one thing we could do is we could say it's half the length of BA. So we could say it's a half times BA. We could also say that it's equal to negative a half of AB. So take vector AB, multiply it by a half, and you've got vector AM, but of course we want, you've got take AB and multiply it by a half, and one of those vectors would be MB, and then if you want the other way around, it's negative a half to get BM. Notice that vector AM and vector MB are equal to each other. Okay, again, vectors have no position. So AM and MB are the exact same vector because they have the same magnitude and they have the exact same direction. And for the final example in this lesson, suppose we've got ABCD being the parallelogram below. Now it is important to know that when you talk about a parallelogram, when you say ABCD, that means that this is A, this is B, this is C, this is D. We usually go counterclockwise. It doesn't really matter if you go clockwise instead. The only important thing to notice, if this is ABCD and this is A, then C has to be here. Okay, it cannot be one of these points right here. So we've got this parallelogram with X and Y as the midpoints of AB and AD. So that makes this point X, and then Y is the midpoint of AD. So this point here is Y. We've then introduced 2 vectors into it too. We've said vector U is equal to the vector from B to X. So we can draw that if we like. That would be this vector right here, vector U. And then V is A to Y. So A to Y is right here. And that is vector V. Express the following vectors in terms of U and V. So vector AD is right here. Well, this is a midpoint, point Y. So this is really just equal to 2 of vector V. That. Okay, vector XA. So XA is right here. And that is actually equal to vector U. So it's the exact same as vector U. It's the same because it has the same length and it has the same direction. Vector CD, okay, notice that vector U and another vector U would be equal to BA, and CD and BA are actually the same vector. So this is just equal to 2U. And finally the last one, CB, okay. Notice that CB and DA are the same vector. So CB equals, you don't need to write this down, but I think I will this time. So CB is equal to DA. And DA is vector 2 of vector V's, but the opposite direction. So this is equal to negative 2V. And there you have it. Okay, so there's some questions for you to try after this lesson. This is all from your Geometry and Discrete Mathematics textbook, which I'll call the Vectors textbook. Page 121, 1 to 6 is simply some trigonometry review for you to work on. Make sure that you're comfortable with the cosine law and the sine law, as well as obviously all your basic trig ratios. And then on page 127, some vectors questions as well. Now, as you're working on page 127, number 2, it's just asking you to decide if something's a vector or a scalar magnitude. Just brush through those questions. It's not super important you get every single one correct. It's not worth, arguing about whether something's a vector or a scalar. It often doesn't matter that much. Okay, that's it for this lesson. Thanks.